Hello, this is Jack Jackson. In this video, we're going to talk a little bit about power series. So polynomial functions centered at x equals a have the form p of x equals some constant c sub 0 plus the sum from k equals 1 to n of some constants coefficient c sub k times x minus a to the k. Or we can say just the sum from k equals 0 to n of c sub k times x minus a to the k if we allow this to be just allow a minus a to the 0 to be 1, which is a little bit of a stretch, but if we allow that, then we're okay with this. And we have seen that if we pick coefficients carefully, then these can approximate a given function well for x values near a. This approximation gets better and better the more terms the approximating polynomial has. That's the idea of Taylor polynomials that we saw in the last video. What we want to do now is generalize this concept of a polynomial further so that instead of finitely many terms, there are now infinitely many terms. This is called a power series. So a power series centered at x equals a is defined to be of the following form. P of x, it's a function of x, right? And it's some constant term, c sub 0, plus the sum from k equals 1 to infinity this time of c sub k x minus a to the k. Or again, if we allow a minus a to the 0 to be 1, the sum from k equals 0 to infinity of c sub k x minus a to the k. All right, so it's just an infinitely many term polynomial, basically, is what a power series is. Well, we got to be a little careful here. When we introduce anything involving infinity, such as a power series, we have to be careful to be sure that we understand the meaning of this construct. In this case, what is meant by a power series? Well, it's a function, so it produces a single output for every input in the domain. So what is the domain and how is the output determined? Well, when we substitute a particular value in place of x, the power series then becomes a series of constants instead, just like that we've been studying in most of the sections of these notes so far. We already know that such a series of constants converges to a single value if and only if the sequence of partial sums converges. So if this sequence of partial sums converges to some limit, then this limit is the output value of the power series for that particular input. So in this way, we see that a power series is indeed a function. However, we now need to consider the question of what the domain of the power series is. When we replace x by some particular constant, the result of the infinite series of constants may or may not converge to a limit. So the domain will be all the possible real number of values for x, such that when we replace x by these values, the resulting series of constants converges. On the other hand, if a particular constant value is placed in place of x, and the resulting infinite series diverges for any reason, then the power series is undefined for that particular x value, and that x value is not part of the domain. So the first thing to notice is there's always going to be one value where the series converges, and namely that's when x equals a. In this case, look what happens. If you put in a here, a minus a is 0. 0 to any power is 0. 0 to any positive power is 0 at least. And so all these terms go away, leaving only the constant term c sub 0. So in this case, the series is c sub 0 plus an infinite number of zeros. So it's just c sub 0. So P of A is always c sub 0. Okay, and that does converge, right? It is defined. So no matter how you pick these coefficients here, and no matter what we have, if we put in a for x, no matter what a is, if it's the same value put in for x, then that power series centered at a will always have at least one number in its domain, namely a itself. However, sometimes that's the only value in its domain, which is not particularly great series then. But it turns out that the domain of a power function has one of the following forms. It's either a set consisting of only the center point A, and we call the radius of convergence 0. I'll explain that a little bit more as we go along. Otherwise, it could be an interval, it could be an open interval of real numbers, say from some number c to d, for some real number c to d, and the radius is the half of the length of that interval. So it's d minus c over 2. So that's what we mean by radius, thinking of this kind of like a circle, but it's actually more like a piece of a line segment, of course. But the radius, it's, so its diameter would be d minus c, its radius would be half of that, half the length of that interval. The domain could be a half open, half closed interval. So it's open on the left, closed on the right. Still same radius, d minus c over 2. Could be closed on the left, open on the right. Or it could be closed on both ends, closed interval. But notice it is an interval, right? An interval there. In the middle of that interval will always be A. In fact, let me add that in here. Okay, this is a little better. So C is going to be A minus the radius. D is going to be A plus the radius. So the radius R is D minus C over 2. So that puts A exactly in the middle of the interval. Okay, and that's true no matter whether it's open on both ends, open on the left, closed on the right, open on the right, closed on the left, or closed on both ends. Or that interval, you can still think of A as being in the center of it, but the radius is infinity, so it goes all the way from negative infinity to infinity, or in other words, it's the entire set of real numbers. We call the radius of the convergence infinity in that case. So the best case scenario would be that the domain is all real numbers, and this function is defined no matter what we put in for x. The extreme case on the other end is that it's only defined at x equals a. That's a not very useful one, but it works. And then all of these other options here, it's some interval centered on a, going r to the right and left of a, but the endpoints may or may not be included of that interval. Okay, so that's the domain. Now, since this is always an interval, unless it's a sort of degenerate interval where it's just one point, this is known as the interval of convergence. And 1/2 the length of that interval is known as the radius of convergence. So one important thing to determine for any function is its domain, and we'll need to determine the interval of convergence for power series that we study. So the domain is an interval of real numbers centered on A. So how do we find out what that radius of convergence is? Well, we always start by using the ratio test. Okay? So we always start to determine the interval of convergence of a power series by applying the ratio test. And when we apply the ratio test to a power series, we'll think of x as being an unknown constant. And in the ratio test, we need to compute the following limit, right? You take the kth term of our sequence, which is c sub k times x minus a to the k. Put that on the denominator. On the numerator, put the k plus 1 term, c sub k plus 1. And then we have x minus a to the k plus 1 power. Take the absolute value, and then take the limit as k goes to infinity. Now notice, look at what always happens here. This is always going to cancel out. This x minus a to the k is going to cancel out with the numerator, leaving only an x minus a in the numerator. The x minus a now has no k's in it, so we can split off the absolute value of that and bring it out front. So it's always the absolute value of x minus a times this limit of the ratio of the coefficients. Now, of course, these coefficients are likely going to be given as some function of k, right? So these are going to depend on what k is. And hopefully we can work with those formulas to figure out what this limit is. Either it doesn't exist at all, or it's 0, in which case we're back up here in the first case where the domain is only the one point A. I'm sorry, if 0, we're actually in the last case where anything would work, because remember, when this is less than 1, then we get convergence, absolute convergence, right? So when this is less than 1, it works. So if this limit is 0 or any other thing less than 1, we can solve this thing, okay? And we can solve this down and figure out what it's going to be, okay? All right. And if it's infinity, though, then this thing is definitely bigger than 1, and so then we're down to this one up here. And sometimes we get some different limit here we can solve for that. We'll look at some examples here in a few minutes. So if the coefficients ck and ck plus 1 are given as some functions of k, then we should be able to compute the final limit above. Remember the ratio test that the series converges absolutely if the limit above is less than 1. The divergence limit is greater than 1. But also remember that the ratio test is inconclusive if the limit's equal to 1. So if this limit turns out to be 0, then you're in this last case. There are no endpoints to worry about. If this limit is some other number, L, then you solve this equal to less than 1. That gives you some interval. That's going to find your C and D here, or your R here, depending on whichever way you look at that. But once we find these C and D here, we don't know. We know it'll converge absolutely on this open interval. What we don't know about is the endpoints. Do we include neither one of them? Do we include just the D, just the C, or both the C and D? And that requires us to do some other test. Okay, so if the limit doesn't exist or approaches infinity, the radius of convergence is 0. The domain is simply the set containing the 1 point. If the limit is L for some positive real number L, it'll converge absolutely when this limit, which is this, is x minus a absolute value times L is less than 1. So basically solving this, we divide by L, we get x minus a is less than 1 over L. So 1 over L is our R, our radius of convergence. So this means x minus a is between minus 1 over L and 1 over L, and we add a to both sides, all three sides, and we get a minus 1 over L is less than x is less than a plus L. So x is between a minus 1 over L and a plus 1 over L. Remember, L was the limit of this part right here, just the ratio of the coefficients. Okay? So we know it diverges when x is bigger than a plus 1 over L. So a plus 1 over L to, I should say, to infinity. It's going to diverge. And then from a minus 1 over L back down to minus infinity, so minus infinity up to a minus 1 over L, it's going to diverge. So it diverges outside of here, converges absolutely inside of here. What we haven't found out is if x equals a minus 1 over L or x equals a plus 1 over L, if it equals one of these endpoints, we don't know what happens. So the ratio test is inconclusive there. So that's why we have to use all those other tests. We have to do something, limit comparison test or alternating series test or something, some kind of one of the earlier tests that we did, all those different tests, we have to test the endpoints, not the ratio test. Okay, so we have to check these endpoints separately using some series convergence test other than the ratio test. We simply substitute a plus 1 over L for x, producing a series of constants, and then we apply one of the series convergence tests that we studied earlier to decide if the endpoint is included in the interval of convergence, the domain. And similarly, we substitute a minus 1 over L for x and apply one of the series convergence tests to determine if that endpoint of the interval is included in the domain. And the end result is an interval of convergence of one of those types that we listed above. It's going to be one of these types here. This one, this one, this one, or this one. Okay. Now, when do you get this one? I've kind of already told you, but that's going to happen when that limit is 0. In that case, 0 is less than 1, regardless of what x is. So the series converges for all real numbers. So we're going to do some examples, a little bit of each type as we go here. Tell you what, we'll pick up that in the next video.